Hello everyone, once again welcome to exciting world of antenna. In last lecture we had discussed in basic antenna concept definition of antenna, that is the introduction of antenna, and second point was different types of antenna, in which we had discussed different types of antennas. For example, lens antenna, dipole antenna, or etc. Maybe different types. Okay, horn antenna. There are different types are discussed. In today's lecture, we are going to discuss radiation mechanism and current distribution on a thin wire antenna. This is the most important concept of the antenna theory. That means how to radiate electromagnetic wave from antenna to free space, and what is the exact mechanism how current will be converted into the electromagnetic wave, what is the sources, what is the radiation mechanism. So before going to the fundamental concept of the antennas, we should be understand the mechanism of the radiation. So directly before going to this radiation mechanism, I am suggesting you that for this antenna lecture series I am using a reference book which is written by Balnis and named as Antenna Theory. So I suggest you that you can use this book for the in detail study of the antenna. Now, one of my first question that it may be asked concerning antennas would be, how is radiation accomplished? In other words, how are the electromagnetic field is generated? By the source. Now containing and guided within the transmission line and antenna, and finally detached from the antenna to the free space. Now the best explanation may be given by illustration instead of theoretical knowledge. Now examine some basic sources of the radiation. Now there are three different basic sources of the radiation, in which first one is single wire source, second one is two wire source, and third one is dipole source. These are the three different sources of the basic sources of the antenna radiation theory. That means how to electromagnetic energy is radiated from the antenna. Now, in which first point is that the single wire. Now conducting wire are materials whose prominent characteristics is the motion of the electric charges. Now the creation of the current flow. Let us assume that an electric volume charge density represented by Q, that is, it is measured in coulombs per meter cube, is distributed uniformly in circular wire of the cross section of area A and volume V. Now the total charge Q within the volume V is moving in a Z direction, okay, with uniform velocity Vz. And if its velocity can be measured into the meter per second, it can be shown that the current density Jz and measured in ampere per meter square over the cross section of the wire, and it can be calculated by using a simple wire equation, and it is L into change in current with respect to Z is equal to, that is length into change in current into the with respect to time is equal to length into the charge into the change in velocity with respect to time, or it is simply product of charge, length and your acceleration. Sorry, product of charge, length and acceleration. This is the equation. Now By using this, simply I can state that to create radiation, there must be a time varying current. There must be a time varying current or an accelerating or deaccelerating of the charges. We usually refer to currents in time harmonic applications, while charge is most often mentioned in the transits. To create charge acceleration or deacceleration, the wire must be curved, bent, discontinuous or terminated. Now the periodic charge acceleration or deacceleration or time varying current is also created when charge is oscillating in the time harmonic motion. It can be seen into the next figure. Now I will show it you after some time. Now some standard assumptions are present for the single wire current distribution, in which first one is, if a charge is not moving, current cannot be created or not radiate. That means when current is stationary, there is no current flow. This is the first point. Then second one is, if the charge is moving with uniform velocity. Now charge is moving with uniform velocity in a wire, but there is no radiation if wire is straight line. This is your point A. Now there is a radiation if wire is curved. Now instead of straight line, if wire is straight line, if wire is curved, bent, discontinuous and terminated, then it may be radiated. Now third one is, if charge is oscillating in time varying, it may be radiate even if the wire is straight line. Now the point 2, in point 2 there is a drawback. If there is no radiation if wire is straight line, but when charge is oscillating in motion, that is time motion, then it may be radiate even if wire is straight line. Now this point is used to remove this drawback. So this is your some points related to the single wire, and this can be seen into this diagram. So you can see that there is curved, there is bent, there is a discontinuous wire, there is a terminated wire, and there is a truncated wire. By using these wires, by using single wire, we can radiate electromagnetic signal. Now a qualitative understanding of the radiation mechanism may be obtained by considering a pulse source. Now this is your pulse source. Pulse source. Here may be connected some pulse sources attached to the open end conducting wire. This is conducting wire, and pulse source may be connected through to this end, which may be connected to the ground through the discrete load in and it open end. So this is your ground. Now when the wire is initially energized, now this wire is initially energized, the charges means free electrons in the wire are set in the motion by the electrical line of force, which is created by source. Now when charges are accelerated in source end, the wire deaccelerated, and negative acceleration with respect to the original motion. Deacceleration means negative acceleration with respect to the original motion during the reflection of its end, and it is suggested that radiated field are produced at each end and along to the remaining part of the wire. Now stronger radiation with a more broad frequency spectrum occurs if the pulses are shorter, if the pulses of the signal are shorter or more compact during while continuous time harmonic oscillating charge produces ideally. Now radiation of single frequency determined by the frequency of oscillation. Now the acceleration of the charge is accomplished by the external sources in which forces set the charges in motion and produce the associated field radiated. The acceleration of the charges at the end of the wire is accomplished by the internal forces associated with induced field due to the build-up of charges concentration at the end of wire. The internal forces receive energy from charge build-up as its velocity is reduced to zero at the end of the wire. That means internal forces receive energy from the charge build-up if its velocity is reduced to the zero at the end of the wire. Therefore, charge acceleration due to the exciting electric field deaccelerated due to the impedance discontinuous. This is your impedance discontinuous or sweep curve of the wire are mechanism responsible for electromagnetic radiation, while both current density, that is a JC, and charge density QE appears at the source terms in a Maxwell equation. In microwave technology, we had discussed some Maxwell equations in last semester also. We can refer this reference book for the Maxwell equation understanding. Now, charge is viewed as more fundamental quantity, especially for transit fields. Now, even though this interpretation of the radiation is primarily used for the transit, it can be used to explain steady state radiation. Now, this is all about the single wire source. Now, second source is the two wire source. Let us consider a voltage source connected to a wire conductor transmission line which is connected to the antenna. This can be seen into this figure. By using this figure, when we apply this voltage across the two conductor transmission line, create an electric field. Between the conductors. The electric field has associated with the electric line of force and which is tangent to the electric field at the point, and their strength is proportional to the electric field intensity. Now the electric line of force have tendency to act on the free electrons associated with each conductor and force them to be dispatched from the antenna toward the free space. Now the movement of the charges create a current that in turn create a magnetic field intensity. Now associated with the magnetic field intensity are magnetic line of force, and also it is tangent to the magnetic field. As like electric line of force is tangent to the, or it is associated with the magnetic field intensity, or it is tangent to the the electric field intensity is tangent to the electric field and which is associated to the electric field intensity, and magnetic field intensity is associated with the magnetic line of force and which is tangent to the magnetic field. Okay, now we have accepted the electric field line start on positive charges and end on negative charges. This is positive charges and end on negative charges. They also can start on positive charge and end at infinity. Okay, start at the infinity and also end at the negative charge, or form closed loop, neither started or ending on the charge. Magnetic field line always closed loop encircling current carrying conductor because physically there are no magnetic charges. In some mathematical formulas, it is often convenient to introduce equivalent magnetic charges and magnetic current to draw a parallel between solution involving electric and magnetic sources. Now the electric field line draw between the two conductors. These are the electric field lines draw between the two conductors to also be Now these two lines are consisting of two different arrows. vertical and downward for the two different charges, that is positive charge and negative charge. If we assume that the voltage source is sinusoidal, we accept that the electric field between the conductor to also be sinusoidal within the period equal to that of the applied source. Now the relative magnitude of the electric field intensity is indicated by the density or bunching. So we can see that there are different number of bunches are generated by the charges of the line of force with arrow showing the relative direction, that is positive or negative, that is positive direction or negative direction. Now the creation of the time varying electric field or magnetic field between the conductors forms electromagnetic wave which travels along to the transmission line, and this can be seen in through this figure. Now the electromagnetic wave enter into the antenna have associated with them antenna electric charges and corresponding current. If we remove part of the antenna structure, now remove this part of the antenna structure from this diagram, and we can get next diagram with this circular loop. Now the free space wave can be formed by connecting the open ends of the electric lines. Now this open-ended antenna is removed, and instead of this line, these lines are present into the now free space, and these open-ended lines are connected by using dashed lines. Now free space wave can be formed connecting to open end of the electric wire. The free space wave are also periodic but constant. Phase point P0, this is P0, and move outwardly with speed of light toward the P1 and travel a distance lambda by 2 in the time of 1/2 of the period. It has been shown into the figure that close to the antenna and constant phase point P0 moves faster than speed of the light, but approaches the speed of light at the point far away from antenna. Now figure 1.12, in this figure, in this display, the certain and travel of free phase wave by a prolate period with lambda by 2 interfocal distance, where lambda is the wavelength, the free space wave of the center fade lambda by 2. This is free space wave which is radiated by the lambda by 2 antenna, that is dipole antenna, expecting the immediate vicinity of the antenna are essentially the same as those of the prolated period. Now the question still unanswered is how the guided wave are detached from the antenna. Now once again go to the figure 1.11, free space wave. Now and water wave created by the dropping the pebble in a clear calm body of the water initiated as some other manners. Once the disturbance in the water has initiated, water wave are created which begins to travel outwardly. If the disturbance has been removed, the waves do not stop and extinguish themselves, but continuous their courses of the travel. If the disturbance persists, new waves are continuously created which lag in their travel behind the others. The same is true with the electromagnetic wave created by an electric disturbance. If the initiated current disturbance is the source is a short duration, the created electromagnetic wave travel inside the transmission line, then into the antenna, and finally are radiated or free space wave. Even if electric source has sensed to exist If the electric disturbance is of a continuous nature, electromagnetic wave excite continuously and follow their travel behind other. This is shown into the next figure. By using this figure of the biconical antenna, we can see that the electric field line of a free space wave, when the electromagnetic wave are within the transmission line and antenna, their existence is associated with the presence of the charges inside the conductor. However, when the wave are radiated, they form closed loop. See, you can see that they form closed loop. Now, there are no charges to sustain. There are no charges to sustain the and existence the electromagnetic wave. Now, this leads us to conclude that electric charges are required to exist the field but are not needed to sustain them and may exist their absence. This is the direct analogy of water wave, which is related to the electromagnetic wave. That means the electric charges are required to excite the field but are not needed to sustain them and may exist their absence. Okay. Now, this is about two-wire source. Now, third source is the dipole. Now, let us attempt to explain the mechanism by which the electric line of force are detached from the antenna to form the free space wave. This will again illustrated by an example of the small dipole antenna where the time of the travel is negligible. Okay, time of the travel is negligible. This is only necessary to give a better physical interpretation of the detachment of the line of force. Although a somewhat simplified mechanism, it does not allow one visualize creation of the free space wave. And this figure, by using this figure, you can see that there is a creation of the three different half cycles, three different waves of the electromagnetic signal. Now, this displays the line of force created between the arms of the small center field dipole in the first quarter of the period, during which the time the charge has reached its maximum value, and it assumes a sinusoidal time variation. The line have travelled outwardly a radial distance lambda by 4. For this example, let us assume that the number of lines formed are 3. You can see that number of lines are formed at 3. During the next quarter of the period, the original 3 lines travelled in addition lambda by 4. That is a total lambda by 2 form a initial point, and the charge density on the conductor begins to diminish. This can be thought of as being accomplished by introducing opposite charges which at the end of first half of the period have neutralized the charges on the conductor. The line of force created by the opposite charges are 3 and travel the distance lambda by 4 during the second quarter. And you can get next one diagram with 6 half cycles. First 3 half cycles are directed upward, second 3 half cycles are directed downward. The end result of these 3 lines of the force pointed upward, that is first lambda by 4 distance, and the second half pointed directed downward, that is second lambda by 4. Since there is no net charge on the antenna, then the line of force must have been forced to detach themselves from the conductor and to unite together to form closed loop. And this can be this can be shown in figure 1.14. See, in remaining second half, the period is same procedure is followed, but the opposite direction. After that, the process is repeated and continuously, identically electric field pattern similar to those of the figure 1.12 are formed. That is figure 1.12 are formed. This is your figure 1.1. Similarly, by using dipole antenna, this figure is formed. So, for this antenna theory, you can refer a book, Antenna Theory, which is written by the Balnis. I suggest you that you can refer this book. Now, next point is the current distribution on a thin wire antenna. Now, this is a two-wire transmission line. In this two-wire transmission line, S is the distance which is used to separate the two different conductors. D is the diameter of that particular conductor. Z is the direction of the transmission. Lambda by 2 is the half wavelength of that particular electromagnetic wave. I0 is the current which is traveling to that particular through that particular transmission line. Now, in the preceding section, we discussed the movement of the free electron on conductor representing the transmission line and the antenna in order to illustrate the creation of the current distribution on a linear dipole and its subsequent radiation. Let us first begin with the geometry of the lossless two-wire transmission line as shown into the figure. Now, this is lossless two-wire. Now, the movement of the charges create a traveling wave current of magnitude I0 by 2. So, this is total magnitude of I0 by 2 along which each wire. Okay. When the current arrives at the end of each wire, it undergoes the complete reflection and the equal magnitude. Then a reflected traveling wave when combined with the incident traveling wave, and it forms a pure standing wave, that is wave pattern in sinusoidal form, and it can be shown in this figure. See, you can see that this is your standing wave. Now, the current in each wire undergoes a 180-degree phase reversal between adjacent half cycle. Okay, this is indicated in figure 1.15a. Okay, this is 1.15a by a reversal of arrow direction. You can see that the arrow direction, this is arrow direction of the first cycle, this is arrow direction of the second cycle. Also, radiation from each wire individually occurs because of the time varying nature of the current and termination of the wire. For the two-wire balanced, next point is, for the two-wire balanced, that is symmetrical transmission line, the current in a half cycle of one wire is of the same magnitude but 180-degree out of phase. Okay. From the corresponding half cycle of the other wire, if in addition the spacing between the two wires is very small, that is S is very less than lambda, the fields radiated by the current of each wire are essentially cancelled to those of the order. The net result is an almost ideal, okay, and not at non-radiating transmission line. As the section of the transmission line between 0 is less than Z is less than L by 2 begin to flare as shown into this figure, it can be assumed that the current distribution is essentially unaltered in the form of each of the wire. However, because of the two wire of the flattered section are not necessary to close to each other, these two wires are not close to each other, the field radiated by one do not necessarily cancel to each other. Now this field radiated by these two wires cannot be cancelled to each other because the distance between these two wires is very long. Therefore, ideally there is a net radiation by the transmission line is present. Ultimately, the flared section of the transmission line can take the form as shown in the figure C. This is the geometry of the widely used dipole antenna. Because of the standing wave current pattern, it is also classified as a standing wave antenna, and if L is less than lambda, the phase of the current standing wave pattern in each arm is the same throughout its length. In addition, specially, it is oriented in the same direction as that of the other arms, and it can be shown into this figure. Now in this figure, you can show that the field radiated by the two arms of the dipole, it may be vertical parts of a flared transmission line, will primarily reinforce each other toward most directions of the observations. Now the phase, due to this relative position of each small part of each arm, must also be included for complete description of the radiation pattern formation. Now, see this diagram, that is current distribution on linear dipole. In the diameter of each wire is very small, that is d is very less than lambda. The ideal standing wave pattern on the current along to the arm of the dipole are sinusoidal with the null at the end. However, its overall form depends on the length of each arm. For center field dipole, with lambda, L is very less than lambda. This is the current distribution for the center field dipole. Now when L is equal to lambda by 2, at that time this is the current distribution, and the symbol, see your symbols are same, plus, and this is the train traveled by that particular electromagnetic wave. Now third one is that lambda by 2 is less than L. Lambda by 2 is less than L, and L is less than lambda. That means the length of that particular dipole is in between lambda by 2 and lambda. The length of this dipole is less than lambda, length of this dipole is equal to lambda, and now the lambda by 2 and the length of these dipoles are in between lambda by 2 and lambda. That means, and this is the current distribution for that particular distance L. Now last one is that is lambda is less than L. Now wavelength lambda is less than L, and L is less than 3 lambda by 2. That means now the dipole length is equal to or is in between lambda and 3 lambda by 2. Now the current patterns are illustrated in for the all that conditions are here. Now the current, by using this current distribution pattern, we can approximately by a triangular distribution, since the current pattern of the very small dipole, usually lambda by 50 less than L less than or equal to lambda by 10, can be approximately by a triangular distribution, since sin KL by 2 is equal to KL by 2. When KL by 2 is very small, this is illustrated in figure like that, here A. Now because of its cyclic spatial variations, the current standing wave pattern of a dipole longer antenna, that means dipole is lambda, that is L is greater than lambda, undergoes 180-degree phase reversal between adjoint half cycle. Therefore the current in all parts of the dipole does not have the same phase. Okay, now this is demonstrated graphically in figure D. This is demonstrated. See, here is a plus, here is minus, and here is plus again. Okay, so this is 180 degree undergoes 180 degree phase reversal between adjacent half cycles. Okay, these two half cycles are cancelled to each other, and these two half cycles are cancelled to each other also. Now, in turns, the field radiated by some parts of the dipole will not reinforce those of the other. As a result, significant interfaces and cancelling effects will not noted in the formation of the total radiation pattern. Now, for a time harmonic variation system of the radiation frequency, that is omega is equal to 2 pi f, the current standing wave pattern of figure 1.16 represent the maximum current exciting the for any time, and the current variation as a function of time on lambda by 2 centigrade dipole are shown in this figure. Now in this figure you can see that 0 is less than t equal to t by 2. Now there are different time constant are present. One is t is equal to 0, another one is t is equal to t by 8, third one is t is equal to t by 4, fourth one is t is equal to 3t by 8, and last one is the t is equal to t by 2. Now these variations can be obtained by multiplying the current standing wave pattern of the figure by using this figure B. We can simply multiply 0.707 into I0 by cos omega t. Now this is all about current distribution on a thin wire antenna. Now the history of the antennas dated back to the Maxwell, who informed that the theories of the electricity and magnetism and represented their relations through set of the profound equations best known as Maxwell equations. His work was first published in 1873, and he also shown that light wave electromagnetics and both light and electromagnetic wave traveled by wave disturbance of the same speed. Okay, so your electromagnetic wave will be traveled with same speed of the light, that is 3 into 10 raised to 8 meter per second, and in correctly it is 2.98 into the 10 raised to 8 meter per second. So up to the now we are completed introduction, types of antenna, sources of antenna, and current distribution mechanism and current distribution on a thin wire. For this in detail study you can use a theory book of, that is antenna theory, written by the Balnes. So this is your reference book which is written by the Balnes, and you can use this book for your in detail study. Now there are some, before going to end of this lecture, I will share something with you that in next lecture, in next session, we are going to discuss fundamental parameters of the antenna, in which especially there are number of parameters are present, in which especially radiation pattern, beam width, lobes, then radiation pattern, that is circular, elliptical. These some parameters will be discussed in next lecture. So don't miss the lecture series, and thank you to everyone. Good day.